Well, it's a pleasure to be here at this very innovative forum. I've already enjoyed it immensely, and I'm looking forward to the rest of it. What I want to talk about is science, engineering, and invention as keys to solving our global problems. I want to draw distinctions between science, engineering, and invention, and I also want to ask, are they creative? Are they going to help change the world? Well, technology sometimes fails us. I'm not getting a response to the changing of the slide. Can somebody give me the second? Oh, there you are. The U.S. National Academy of Engineering, at the beginning of the new century, organized a committee made up of scientists, engineers, and inventors, and asked what would be the grand challenges of the 21st century for engineering. And they came up with a very interesting list, and they called them, change the slide, grand challenges for sustainability and other categories. There are 14 challenges in all. I just want to emphasize a few of them to draw some points. The next slide emphasizes the next slide. Well, we have a problem. The next slide, please. Make solar energy economical is one of the challenges, for example, and I think this is a very familiar challenge. The science of photovoltaic cells is widely known. This is not something that needs basic research at this point. So it's fundamentally an engineering, economic, environmental, and other kind of problem that has to be addressed. Science tells us a lot of what we know, but it doesn't help us change the world in fundamental ways. The next slide, this is an array of solar cells, as we've seen in a previous presentation. The sun shines most brightly in desert areas, remote areas, areas that don't really need electricity. Also areas that environmentalists want to preserve. The next slide is an alternative to photovoltaic cells. It's really very conventional technology. You array a bunch of mirrors, you focus the sun's rays up to what is essentially a tea kettle, you boil the water in it, you generate steam, and you generate electricity in a rather conventional way. There are many other options for generating solar power. The next slide shows us one of the problems, however, and that is, how do you get the energy from where it's produced to where it is needed, namely in urban areas? Well, obviously you need power transmission lines. This also meets up with some human environmental challenges, and that is that people don't want these lines, and they generally are considered unattractive, not pieces of technological art, although they could be, and there's room for creativity there also. But perhaps more importantly, what happens when the sun goes down? The sun doesn't shine 24 hours a day, and yet electricity is needed 24 hours a day. In many solar installations, the problem is that you have to have a backup system, which usually is not green energy. The next slide, other grand challenges that relate to human health. And the next slide, one I'd like to emphasize, the next slide, the infrastructure, the urban infrastructure in many places around the United States is really deteriorating. It's over a century old. It spontaneously breaks, it spontaneously puts people out of touch with essential sewer lines and water supplies, clean water supplies. How to attack a problem like this is more than just a technological problem. It's a political problem. It's a human problem. The next slide talks about grand challenges for achieving security and the joy of living. This was a category that was introduced by this committee. The next slide engineering the tools of scientific discovery, and this is bringing me to the core of my talk. Science needs engineering almost more than engineering needs science. The Large Hadron Collider is the biggest particle accelerator in the world. It recently opened up in Switzerland, and after some troubles, as many of you may know. But the Large Hadron Collider is supposed to reveal secrets of the small particles that will help us understand how materials behave. Information that engineers need to know to develop better materials and build things like the Large Hadron Collider. So it's a rather circular system. The next slide. The technology has always led science. The telescopes that Galileo used to explore the universe and write about it were really of a technological design, not a scientific design. The Hubble Space Telescope that went beyond the atmosphere to see more clearly things that Galileo couldn't see is also an example of that, an ongoing example. The next slide. Who's going to take up challenges like this? These are clearly grand challenges for engineering and really for the world. Well, scientists, engineers, and inventors are obvious choices, obvious expectations. But what about entrepreneurs, venture capitalists, industrialists, and so forth? What role do they play? Well, they play a central role because everybody needs support to carry out research and development. In fact, all of the above will really be necessary. The next slide, we go back now, you got me. There must be collaborations among groups and even within individuals. People, whether they be scientists, engineers, or whatever, have to be able to think more broadly than just within their own discipline. The next slide is an example of what I mean. Theodore von Karman was a very significant rocket scientist, literally a rocket scientist. He was an inventor, he was a scientist, he was an engineer. He happened to be educated as an engineer, so some people like to claim him as that. A lot of his work actually was closer to the scientific method than to engineering. But he exemplifies the kind of people that will take us forward in technology. The next slide is a quote from von Karman. And I talk about him and I use his quote because he obviously had insight into both science and engineering. Scientists seek to understand what is, von Karman wrote. Engineers seek to create what never was. That's a very, very fair distinction, and I'd like to elaborate on it. Next. A scientist deals with existing things and phenomena, seeks understanding of those things that he or she chooses to study, frames hypotheses about them, and that would be said to be one of the central ideas of science, is framing hypotheses, coming up with an idea and then testing it, testing those hypotheses, presenting the results to scientific peers, writing reports, publishing papers. Invention, well, sometimes scientists believe that that's impure. That's not pure science, so they ignore it. The fact of the matter is that just this week, these previous weeks, the climate change issue, global warming, has really illustrated the problems with some of the scientific approaches. The next slide. So is creating a scientific hypothesis doing science or engineering? And I want to emphasize here how confused the ideas can be. Before being stated, a hypothesis does not exist in the form of a hypothesis. Well, according to von Karman's idea, that's more doing engineering then. So although scientists think in many cases that they're superior to engineers, in fact, some of their most exquisite science is a form of engineering. They create a new hypothesis, and that's akin to inventing a new thing, the hypothesis being the thing. Testing a hypothesis is an application of the scientific method, and a key application. Designing experiments is also doing engineering. In fact, whenever you see the word design in a technological context, it really should signal engineering. And publishing is like patenting. So science, engineering, technology, invention, innovation, although we use different words, we think of them differently. In fact, they're very much convoluted. And in going forward and trying to get ideas that change the world, that people and teams have to be prepared to think on several levels. So let's go to engineers now. Science seeks to understand what is. Engineers seek to create what never was. I think this is working now. So engineering seeks to create new things closely linked to invention, has an element of art to it, but is not art for art's sake. Engineering also always has an objective, which is more than itself. But there's also an artistic component to engineering, especially in the process. It's a creative process. It also has an element of science to it, but it is not simply applied science, and I'll elaborate on that. Engineering has there are several examples of engineering being more than applied science, because the science simply did not exist. And these include the steam engine, powered flight, rockets, computers, the moon landing, science, selective breeding preceding genetics. All of these examples were engineering achievements before the science came into existence in a full way that could really explain things. In fact, it was the engineering achievements that drove scientists to seek theories to explain. So, are engineers and scientists defined by their education or by their work? And here again, I think, is an opportunity to gain some insight into how do we classify people? How do we put them into job slots? How do we work with them? How do we assemble teams? And we don't want to be misled too much by a degree. An engineer can act like a scientist. A scientist could act like an engineer, and a scientist or an engineer can also be an inventor. And the next slide shows some data on this. The National Academy of Engineering elects people to its membership for their engineering achievements, or their achievements in engineering, if you prefer to look at it that way. In fact, in the class of 2009, which consisted of about 65 Americans, 1 in 4 had no engineering degree. And they were people who studied in college, math, chemistry, physics, computer science, and yet they achieved things that were considered greater engineering achievements than many engineers. 3 or 4 of these people elected had patents, so that they just didn't think of these things abstractly. They thought of them as true innovations. And the rest of the data just illustrates that engineers and scientists can belong to each other's academy, and that just emphasizes further. Oh, thank you. I needed that. Thank you. Okay, so let's go to the next slide. Next slide. Okay, this is a very interesting image. This image of a scientist and an engineer, we might say a typical scientist and a typical engineer, or an atypical one, however you choose to interpret it. But it's an image of Albert Einstein and Charles Steinmetz, and I'll say a little bit more about each of them in a minute. But this image can be taken as emblematic of science and engineering. Science stands tall. It generally has greater stature in the minds of the public and of politicians. Engineering, on the other hand, we don't want to go too fast. Engineering, on the other hand, is of a lower status than science, and generally is not considered to be as sophisticated, shall we say. We see Einstein here. He's well dressed. This is Charles Steinmetz, who, well, you might say he's well dressed or you might not, depending on how you look at these things. But Einstein looks like he's dressed for the winter. Steinmetz looks like he's dressed for the summer. We all know that Einstein was a scientist, we might say, the prototypical scientist. But I'm going to show that Einstein was also an inventor, a serious inventor. Steinmetz started out as a mathematician, yet he became known more as an engineer and an inventor. Next slide. We all know the story of Einstein working in the patent office. He started out there, and it's less well known that the reason he did that was that he couldn't get a job teaching, which is what he wanted to do. And the reason he couldn't get a job was he wasn't that good a student. So he took this job, and many people, the conventional wisdom is that he really suffered through that job of examining patents. The next slide. Actually, what Einstein believed was the formulation of patent statements was a blessing to him. It gave him time to think about physics. So this is a guy who could have been bitter. He could have said, this is ruining, my creativity, my innovative spirit, and so forth, but he didn't. The next slide. In 1 year, while he was working at the patent office, Einstein came up with 4 ideas that he wrote papers about on light quanta, Brownian motion, special relativity, and the equivalence of matter and energy. 4 world-changing ideas. And actually, Einstein thought of these things more as inventions than scientific theories. The next slide. Einstein and Szilard were partners in invention. The next slide. They looked upon the situation in the 1930s with refrigerators. Refrigerators were new then, especially electrically driven ones. And the problem was this, the next slide. The refrigerants used were poisonous. If there was a leak in the refrigerator, the poisonous fumes would be released, and as a result, people could die, especially if the leak developed overnight while everybody was sleeping. The next slide. Einstein and Szilard believed there had to be a better way, and they came up with that better way by eliminating the mechanical pump altogether. They substituted a source of heat for a source of mechanical energy. It was really an innovative, world-changing concept that would have eliminated the poisoning of people and would also have eliminated noise that refrigerators make, which everybody knows can be very annoying. Go ahead, next slide. Einstein and Szilard actually took out a patent. This is the US version, but they took it out internationally. And they were serious inventors. They weren't just doing this on a lark. They made a formal pact with each other about how they would divide the proceeds of this invention when it became an innovation and everybody wanted these refrigerators. And it would have gone that way had Freon not been developed about the same time. And Freon was non-poisonous. As a result, you could just stay with the conventional refrigerator, substitute the poisonous refrigerant with Freon, and just go on with the technology as it was. In fact, companies did that. They chose to not retool. They chose rather to just make this modest change. Now, as everybody knows, Freon, decades later, proved to be a very harmful product for the environment. And of course, now refrigerants no longer are Freon. Next slide. For Einstein, a hard and fast line between technology and science simply did not exist. Einstein enjoyed inventing as much as he did doing science, as much of a scientist that he was. Now, these stories are not widely known about Einstein, and I think it's in part because scientists want to preserve this mystique about themselves in their field. The next slide, Einstein reflected on science as opposed to invention. And he criticized Ernst Mach, who was a philosopher of science. And what he said, and the bottom is the last thing, is the most important thing. Mach thought that somehow theories arise by means of discovery and not by means of invention. In other words, Einstein believed that scientists invent new theories. And this comes back to what I said earlier, that science in many ways is like engineering. Or in other words, there's very little difference between them when you get right down to it. And we shouldn't favor science over engineering. If anything, we should do the opposite. The next slide. Okay, so back to science and engineering. Einstein and Steinmetz, if you will. And I use this because Einstein and science were inseparable in the conventional wisdom. The next slide, I'll talk about Steinmetz for a minute. And again, the next slide. Steinmetz, the word Steinmetz, the name Steinmetz, became synonymous with engineering. Steinmetz engaged in some of the early radio broadcasting. He talked about technology. He talked about innovation, what was happening at the time. Next slide. He was also recognized as an inventor, just again to further emphasize that there's this convolution of all these things. Next slide. What is the difference between an engineer and an inventor, such as Steinmetz? Well, there is an actual patent that I quote from here, and the inventor is saying, he's describing his new device, and he's saying, whatever the reason it behaves as it does, it is extraordinarily well adapted to the purpose. In other words, he's saying, this thing works, that's all you need to know. An engineer wants to know why the thing works, because by knowing how and why the thing works, the engineer can make it better, can improve still more on the technology. Next slide. Steinmetz was famous for promoting himself and General Electric, or perhaps it's fairer to Steinmetz to say that General Electric was famous for promoting Steinmetz. And whenever there was an opportunity for Steinmetz to pose with a famous inventor, especially a famous inventor, the GE was there to take a picture. So Steinmetz met Edison, Steinmetz met Marconi. Now it's very interesting that both Edison and Marconi were inventors first and engineers or scientists remotely, if even that. In fact, Marconi, dealing with early broadcasting, didn't believe the scientists who said it can't be done. It violates principles of physics to send radio waves across the ocean, for example. Throughout the history of engineering and technology, there have always been naysayers among the scientists, not among the engineers. And some people, of course, say the less you know, the more you can achieve because you don't know what you can't do. The next slide, comes back to this photograph. The reason that General Electric was so interested in this photograph is it was a further indication of Steinmetz's broad interaction with the scientific and inventing community. Now, I want to go from this to look at research and development, because in certain ways, science and engineering is synonymous with research and development. Next slide. Meeting and posing for pictures together does not in itself constitute collaboration. That's a trivial observation, but I just want to make it. Just because people seem to be even on the same team doesn't mean they're collaborating in any fruitful or significant way. Further, do research and development teams engage in fruitful collaboration? Well, that depends, and I'd like to talk a little bit about that. Next slide. Early research and development labs in the United States are listed here, some of them. Thomas Edison was famous for having his own research lab that later developed into what he called an invention factory. He had a staff, and their idea was to turn out inventions of all kinds as fast as they could. Westinghouse and General Electric were competitors in the early days of of electricity. Westinghouse was the alternating current, and General Electric was the direct current for a while. It was Steinmetz who actually convinced General Electric that it was important to look at alternating currents as the way of the future. In fact, so much of Steinmetz's mathematical work underlying his engineering was in figuring out how to send electrical alternating current efficiently over transmission lines. Other companies started research and development labs at the same time, or about the same time. At Westinghouse and General Electric, it was driven by product development, or engineering, we might say. It was engineering that drove the process. For something like Kodak, it was science, because Kodak with film and was so closely connected with chemicals, you had to have a fundamental chemical understanding for progress there. So whether you emphasize the science or the engineering depends to a large extent on what your company is doing. The next slide. Why were they doing industrial R&D? Why was it blossoming all at the same time? Well, they were interested in new product development. At the same time, they wanted to keep competition at bay. And they wanted to avoid antitrust suits, that they were all in collusion. So they internalized the innovation process. Each company, even though they'd be in the same field, was looking inward and trying to come up with competitive ideas. They wanted to diversify their product lines also. The next slide. But research and development then comes in many different flavors, many different colors, many different styles. You can't say that if you look at Westinghouse and see its model of research and development, that it tells you a lot about Kodaks. There's no connection. So looking at a successful model in one company doesn't really tell you very much at all. The next slide. The ampersand, the and in research and development is actually the linchpin connecting these two halves, if you will. It's the fulcrum about which research and development turns or balances. The next slide. So this, how you connect research and development, how you pass between one and the other, depends very much on whether you emphasize the research or you emphasize the development. And this has been a tension for a very, very long time. Next slide. After World War II, when the scientists clearly played so much of a role in developing a new weapon, they developed what was known, and still is known, as the linear model of research and development, the linear model of R&D. And that was that you do basic research, and that ultimately leads to the development of innovative processes and products. Science precedes engineering. Now you remember I've given many examples where that's simply not true, but just about everybody who was in a policy-making position in the post-war years in the United States was thinking this way. The next slide. Not only thinking this way, but also allocating resources based on this kind of thinking. But there was a project in the 1960s called Project Hindsight, about 20 years after all of this thinking began, that said, well, is this really true? A good question. And they found, basically, to summarize this, that it wasn't true. They could find only a minuscule number of examples where the basic science actually led to something that was technologically innovative and useful and desirable. Next slide. So this influenced how in the United States the research and development budget evolved. Back in post-war years, the federal funding for research and development was largely science-based. But after this recognition that there is a limit to how much you should put into science with the hope or the promise that it's going to bring development in technology, began to change. And then industry began to expand its contributions to research and development because they couldn't count on the government to do it. And besides, they didn't think, after all, the government was giving the right emphasis. Next slide. So R&D is a very complicated pair of letters connected by an ampersand. The next slide. Research and development, science and engineering, engineering and science, development and research, or research and development and research, development and research and development. Which is it really? What really is the way it happens? What really is the way to create new ideas that are going to really change the world? It's not at all obvious. But the weight of evidence, if you look at it closely and you look at it without prejudice, it appears that development should precede research. We shouldn't speak of research and development. Perhaps we should start thinking and saying development and research more, because it's the development concept, it's the development goal that actually selects for you what kind of research should be done. The next slide. Lost track of time. Looking for my signal. I think I'm okay. So things are not always as they seem. We get in the habit of saying R&D, of writing R&D, of thinking R&D, when in fact that might be getting the cart before the horse. Next slide. Just to emphasize this, that things are not always as they seem, let's look again at this General Electric publicity photo of Einstein and Steinmetz from 1921. When I was writing a book in the 1990s, I wanted to use this photograph to illustrate a point. So I wrote to General Electric, to their publicity department, and asked for a copy of the photo and also for a permission to reprint it. They sent it to me, no questions asked, and granted permission. The next slide. The photo was actually a phony. Here's a meeting in 1921 when the so-called photo of the joint meeting took place. It was really a group photo, and Einstein and Steinmetz just happened to be standing near each other. They were not having a one-on-one conversation. They were not discussing how science or invention could help technology or vice versa, or any combination of those things. The next slide. General Electric took part of this photo. Next slide. There was an interloper between them. The next slide. He was erased, and we end up with the famous photograph. Now, General Electric certainly knew this because they did it. But they were so focused on promoting a concept, promoting an idea, promoting an individual who so much symbolized General Electric that they lost sight of the goal of honesty. This photograph, to the best of my knowledge, General Electric has still not admitted to this in any big way. The next slide. So, just because people are members of a group, as I said earlier, doesn't mean they're necessarily collaborating. Doesn't even mean they're talking to each other. But that's often the perception. So if we have objectives, if we have a group, we have a team, we have a research and development staff that we expect to be doing something, just because they appear in the same organization chart, or just because their names are part of the same caption of an annual photo, let's say, doesn't mean we're achieving the ends. We have to look at collaboration anew, afresh. We have to look at it in terms of results, in terms of output, in terms of reality, really. Classifying people too rigidly can stifle progress in science, engineering, and technology. Just because somebody has an engineering degree doesn't mean that that person can't be an inventor. Just because somebody is a scientist doesn't mean that person can't be an engineer or an inventor. And all combinations apply, actually, although it is harder to go from being an inventor to being a scientist or an engineer, because those usually involve some formal training that being an inventor simply doesn't have. The next slide. So, if we look at this, it no longer should symbolize to us science stands over engineering. It's a lot more complicated than that, and we should recognize that. The next slide. The lines between inventors, engineers, technologists, scientists, entrepreneurs, however long you want to make the list, are at best blurred or dotted lines. They are not solid lines of division. So the talk about collaboration can be really much more significant if we recognize that. Next slide. Let me just say in closing a few words about complex problems. It's almost obvious that complex problems require complex approaches towards solutions. Next slide. Even some of the most familiar technologies can prevent complex challenges. How can we make a better light bulb? Light bulb, the virtual symbol of getting an idea. Next slide. In many countries around the world, the incandescent bulb, which had a long life, is marked for extinction. There are political bans on selling these things after 2014 in most countries. So the compact fluorescent bulb, which was actually developed back in the 1970s when there was an energy crisis, but wasn't manufactured until the 1990s because the energy crisis went away, and of course then the bulb was put in the drawer. This is also another little lesson that just because situations change doesn't mean that if you've got a good solution, you should put it away because the situation has changed. You should go forward with it. But anyway, the compact fluorescent was thought to be a very good solution, and it's its existence that led to the banning of the incandescent bulb. But as you probably know, not too many years ago, it was discovered that these compact fluorescents have the very dangerous element of mercury vapor in them. So when they break or when they are being disposed of, they really have to be taken care of rather elaborately. Furthermore, compact fluorescents, although they had showed early promise, they never did achieve the brilliance, if you will, of the incandescent bulb. They didn't have the same kind of light. They didn't have the same kind of lifetime. The latest is the light-emitting diode, which has developed sort of in parallel with the compact fluorescent. But the light-emitting diode has always been more expensive. But now that the mercury situation has been discovered, everybody is throwing their weight behind the light-emitting diode. Philips Lighting, for example, has taken all of its R&D money out of making a better, more pure light, compact fluorescent, and making it into, putting it into LEDs. The next slide. So as I started with, what happens to wind and solar power when the wind stops blowing and the sun sets? Next slide. Well, people say a smart grid is the answer. A smart grid that will recharge automobiles and sometimes let the grid feed off the battery storage power of the automobiles, the all-electric automobiles. Next slide. But what kind of R&D will result in better storage batteries? Storage batteries have been around for centuries. I think it was Benjamin Franklin who coined the word battery. But we still don't know how to make a really good, inexpensive battery. But what's going to do that? Is it going to be basic scientific research? Well, we could say the basic scientists have had 2 centuries at that. Is it going to be engineering based? Well, it has to be. Engineering is about developing more efficient, more economical products. It has to be focused development. Government sponsored? Well, the government in the United States is starting to put a lot of money into battery research. Is that going to be the answer? We shall see. It's not clear that it's been the answer in the past. Will academics or industry lead in this development? That also is not clear, although most people would probably bet on industry. Venture capital will have to do some supporting if it's going to be startup companies. Inventors in their garages have come up with a lot of good ideas in the past. Maybe that's where the next good battery is going to actually come from. Next slide. So this is, well, that's okay. This is just a rehashing that when the lights go down and the wind stops blowing, nuclear plants and coal-powered plants are going to feed into the grid. They have to. That's the backup. It's going to have to be that way, at least under the current paradigm. Furthermore, something like solar, just as an aside, there are communities out in Nevada which have a lot of sun, and there's a great deal of interest in putting large solar farms in that sun. But in order to keep these solar panels efficient, or even the solar mirror technology, a lot of water has to be used to actually clean them regularly so that they operate at peak efficiency. But in some cases, the best place to put a solar farm is in a county where the maintenance of the solar farm would consume 1/5 of the water available in that county, which is not sufficient for the county as it stands. Next slide. So sustainable energy issues are going to have to involve a lot more than just science, engineering, R&D, invention. And this is what I interpret this conference to be all about, this forum. Have to recognize that there are questions of the environment, there are questions of land use, there are questions of ethics about who gets to use water when. Next slide. So the wind farms and other renewable, clean, green energy sources are not necessarily going to be the answer to our problems. And whether green energy jobs are going to really be economy saving also is open to question. Next slide. So technology plus, the plus to me means just about everything. Technology plus people, collaboration, society, and art, as we've heard in several occasions this morning. And then the next slide. What will be the face of successful research, the successful research team of tomorrow? Will it be the group that has a lot of very fancy names attached to it? Einstein and Steinmetz, let's say, where in fact they are contributing very little to the group itself? Or will the team of the future be more anonymous people that truly do work together and work seamlessly, and where no one necessarily stands higher than the others? This goes back to the early experience with research and development labs, and this argument was happening a century ago, literally, believe me. Next slide. So technology plus research team, technology research team has to have all sorts of people, and increasingly there is talk about people outside the technology arena. Even in Washington, D.C., this kind of talk is gaining momentum. Next slide. The technology teams, the technology plus teams, will be international. They'll be diverse, they'll be non-traditional, and they'll be creative. And the creative part is probably the most important component. The next slide. What will drive the technology? Well, I started out by talking about the National Academy of Engineering's grand challenges. Setting out problems, challenging the technical community as it stands today to approach these problems in a serious, dedicated way. But there'll be competitions. Competitions are a new way that is well, I shouldn't say a new way, a way that has been renewed, revitalized, where somebody says, okay, we need a bridge here. We would like teams to compete with designs for that new bridge. We'd like them to be innovative. One of the ways we think we'll get that is by having teams that are innovative. We want the teams. The teams must have both an engineer and an architect as members of that team, for example. And in some cases, they must also have an artist. And these have actually revealed some of the most elaborate and creative designs of bridges in a very, very long time. Prizes. The idea of prizes is an old one also. There was the Longitude Prize back in the 17th century. Charles Lindbergh made the first transatlantic solo airplane flight by being challenged by a prize that gave him $25,000 for being the first to achieve that. Increasingly, there are prizes being developed to create new batteries, more efficient batteries, better solar panels. Just about you name it, there is a prize for it. And I think that given the time constraint, this would be a place for me to stop, because this sort of summarizes what I've been trying to emphasize in this talk. I will say that I'm going to talk about bridge competitions in my lecture this afternoon as an illustration of how teams, diverse teams, can actually come up with really world-changing designs for one technology at least, and that is highway and transportation bridges. Thank you very much for your attention, and good luck with the rest of the forum.
헨리 페트로스키 교수의 기조 연설이었습니다. 다시 한번 큰 박수 부탁드립니다.